Hello everyone. So today we'll be looking at how to improve a pulse oximeter uh, signal processing simulation. So in my first year physics engineering project, I had to build a pulse oximeter with two colleagues of mine at school, and the actual physical device ended up having a lot of bugs, and we couldn't get relevant outcomes. So, in the last minute effort, I tried to pull out a simulation to try to show that if we were to get the right, the right, if we were to get the right uh, signal in, we could actually, as you can see here, could actually show the right outcomes. We could get here you can see the heartbeats, get how many beats per minute, and what's the oxygen saturation. So, but now I'm trying to apply to a research team at my university who are working on machine learning applications for, um, well, more like mathematical modeling, and they're currently looking into how we can use machine learning to improve mathematical modeling of engineering or other physical processes. And basically, we're looking for improvement in speed processing or quality of output because most of the problems we're looking at already have solutions. So we want to see if we could get better solutions with machine learning. As a research team, our goal is to improve our understanding of the tools, not necessarily to actually find a solution per se, but to find a hint to the solution. And as a first year going into a second semester in physics engineering, it's a big challenge for me to actually show a project that works and that is up to the standards of a simulation where I could actually use machine learning and help them out with the mathematics. So let's look at what my plan is. So my deadline is 10th of January. I'm supposed to show on the 10th of January 2024 my simulation. So 10th of January, that's the deadline. And we are currently on the 1st of January 2024. So which means I have 9 days to do so. Yes, I procrastinated. Yes, I am late. But who cares? Well, I care. But whatever. We can't do anything about it right now. We need to get things going. So what are the steps? First, I need to map out my current simulation. Second of all, I need to find the relevant mathematics, physics, and functions that can, well, it's not that they can predict, but that should predict, should explain the so that should explain. We have two things that they should explain. First of all, current outcome, current output, current output. You can see the dyslexia here. Output and the theoretical. So we know what it is supposed to output. We want to know how far are we from that ideal and why are we that far. So these are my first parts, and then we need to change the simulation, the sim, to get a decent output with decent output with the right answers, with sufficient understanding of the program. So if I can pull this off, I have a bonus additional step. So here, this is the bonus. Probably going to work on it anyway, even after the deadline, which is to have a full documentation of the project. Okay, so yeah, this is what we're gonna work on. Okay, so let's get started. Let us map the simulation. So we need to map. So I've already kind of mapped it here, but I'm gonna go through it again. So here we have the imports. So within the imports, um, we have NumPy, Matplotlib. We use especially pyplot, nothing else. We have SciPy. We use especially Signal and FFT. Secrets, Serial, and another serial tool. So right now, in the simulation, we don't use serial. Serial is supposed to be a way to communicate between the ports of the computer to actually link Arduino with the actual simulation. I will have a video talking about how an pulse oximeter works and how this is relevant for the project. So first, we define a few functions. These functions play a critical role in the outcome of my program. So I have three main functions. We have the signal simulation. So we sorry for that. So we have prepare functions. So I'm going to put big one. This is within functions. We have big one, uh, signal sim. Big two is signal analysis, and big three is SO2 calculation. And here we have BPM. So we extract the BPM from these. So here, this just means the signal simulation is what my device outputs into my computer. So we do a simulation of the output, the input in the program. So my program should get an input that represents the information given by my pulse oximeter. This is the input, and this input is actually related to, how does this input relate to my simulation? Oh yes, this input has to have noise. Well, in the most ideal of worlds, in another simulation somewhere, my input does not have noise, and then I would not need to do any programming whatsoever. However, there is a lot of noise, there are a lot of interferences with my signal, and you'll know why, because I haven't done that other video yet, but there's noise. And we need to explain, um, so we need to explain how we build that noise. So build how to justify it. And we need to have a range. So for the noise to be relevant above a certain threshold, we cannot read the output, the input. So we're looking for a very distinct signal, just a little thing right here. We're looking for like this signal here. This is really wrong. I'll just show you an image. Probably link it. I'll link all the images later on, but basically, if you go here, as you can see, we're looking just for this orange bar, which is the actual frequency we're looking for. So yeah, we also need to explain in the above signal so how the convolution works. There's a certain convolution, so I need to explain how the convolution works and how we add the randomness to it. So here we need to also explain y convolution and how built. These are the main issue, and then we need to relate how does the noise build into this. As for the signal processing, this extracts, well, relevant frequency the relevant absorptions, and that's the main thing of light. Yeah, that's the main thing. And here we use what, so these are then inputted here, and they give us the SO2 saturation and the BPM. And then we should, so this is the functions. Then here, what do we do now? Let's see, I've kind of forgot. So this, you can see, we use everything, then we plot. I need to explain. So then there's, within the functions, we have a second category, which is for just plotting. And we need to understand the limitations. Oh, and here we also need to identify. So basically the main goal everywhere is always going to be identifying. So here when we map, our purpose is to find a percentage of accuracy, a percentage of precision, and we want it to be as close to optimal or close to the current limitations. Because say you make it very accurate, so you make a perfect signal that is inputted, this would not make the calculations relevant. You need a similar accuracy from a good to average pulse oximeter so that you use the correct information to test your model that should not be impacted by how the signal comes in. It will be, but you should have some buffer. And so here we need to also understand how this, so how errors propagate. So here, the second thing is error propagation. Now that's important because if you don't understand error propagation, you can't present your work. you also need to identify the mathematics and physics behind these things. Maybe you're using the completely wrong models. So here we need the math. Usually it's related to computer science, algorithms, or limitations of the machine. And you also want a physics understanding of the actual tech, the physics behind it. So it's the actual tech. Well, the physics will also help you understand the limitations of the computer science to the math, and the math help you understand the physics. So they're really they complement each other. Plotting, there's the same thing. You're using pixels. Pixels are limited, and they are a digital form, so there is no in between. It's very accurate, but it's either 0 or 1 or an approximation. So you can have many zeros, many ones that would make it 0.1. So the fifth part is going to be the parameters. So this is important. We have parameters, and these parameters, I I honestly understand them very little, but they determine how the whole system behaves. So I'm assuming a starting position. This is probably my weakest link. I'm assuming a certain starting position to make this all work out. If I change the starting parameters, things don't work out so well. I need to understand how each variable in my parameters affects the whole simulation. Either propagates error or gives irrelevant results. So here we have, so this is a new part. Here we enter the actual simulation. So this is no longer functions, but the parametered simulation. So here we have the parametered simulation. When we look at the parametered simulation, we need to understand that we have parameters, and I'm gonna have to map them out, but our purpose is, so this is probably very important, so I'm gonna go in red. Just remember that it's important. And here we are looking at, so I imagine these are the parameters, how each p for parameter affects p, this is effects, or p affects out, so it affects the output. So let's look at our parameters. I know there's duration, there's time, so we have duration, sample frequency, noise level. Okay, so we have duration in seconds, sample frequency, I don't know what we use it for, but this is something that I need to understand. Now it affects a lot. So we have noise level, we have T, which I don't know what T is, but it's supposed to represent time. So this is a, I don't know. So instead of this, I'm gonna put in yellow because that's important. I don't know. I also don't know what this does. I have, yeah, so the noise level is the uh, intensity of the noise. So here it's intensity. Ah, it's in the noise level. So here I need to find the range. I need to find the range. Then I'm gonna need to look at T. I don't know what is T. I feel like it's an array or something. And what does it do? Yeah, I know this what this does, but then again, I also have the wave frequencies. So I also need the range for the wave frequencies and the sinusoidal frequencies. So the square wave frequencies and so I'm gonna put square waves uh, should be uh, frequency should be in rads per second. I don't like putting rads per second. I'm a -1 person. And so we need to understand the range, and we also need to understand what is the sinusoidal frequencies. What are they? You need to understand the functional range. So this means this means functional okay. Then we just use our functions. Then we print out the results. And after that, we plot the results. So here there's the display of results. And we're done. So it's not that hard. So after that, there's just apply, parameters to functions, and how parameters affect functions. So apply to functions, and then we have display output. An interesting part of here, I think this one is also very important. This is kind of the basis of the whole simulation. We're simulating the real thing, and then after that, it's actually a pretty straightforward process. So for number one, I think here an interesting thing to look at is how does the Arduino and plus port transfer, how do they affect input? So this ends our lesson for today. We just mapped out the whole process. We have our deadlines, we have our map. This is the process. And so we need to understand every nook and cranny of this four-step algorithm. Well, it's actually a three-step algorithm. Functions, plots, no, it's a functions, parameters, display. And within the functions, we have many intricacies. We want to look at the accuracy and precision, the error propagation, and we want to look at how close it should be from the optimal result and how close it should look to the limitations. What are they? We need to be able to understand that's the most important part within the whole report, because I'm applying to a math research center, the maths, the physics, and the limitations of computer science. So these are my priorities. After that, we need to make it functional. But for the moment, this is where we are at. So, thank you for listening, and I will see you next time.